Hello, class. This is chapter 25, fluid, electrolyte, and acid-base homeostasis. These are things that we've sort of addressed in other chapters, but sort of pulling it together because balancing your fluids, basically your water, balancing your electrolytes, your sodiums, your potassiums, your magnesiums, your calciums are very important. And also balancing your acid and base. Remember, the body has to stay slightly basic, 7.4 pH has to stay slightly basic and has to stay there at all times. All right, so chapter 25. All right, the body's fluids. We have blood plasma. Clearly, your blood is primarily made up of plasma, which contains proteins, platelets, water. Interstitial fluid, the fluid between cells. We have cytosol, the fluid that is in the cell. Cerebrospinal fluid surrounding your spine and your brain. Lymph. Remember, once fluid is removed from your bloodstream, fluid that comes from the bloodstream travels to the lymphatic system and becomes lymph. We have exocrine secretions and other specialized fluids. But all of these fluids in the body are water based. We are primarily made up of beautiful compound known as water, H2O. And so we study fluid balance, which is largely studying the water balance in our bodies. Our bodies have to have a certain amount of water, have to have a certain concentration of electrolytes, acids, bases, and any imbalance can cause some serious problems. Functions of water in the body. Remember, water is the universal solvent. So water is very important in that regard. You can transport a lot of things with water because it dissolves in water. Water distributes body heat. Um, we can sweat, as everybody knows, and the evaporation of that sweat can cause our temperature to go down, for instance. Water can help cushion organs because we have water constantly in our bodies, so it causes we're sort of bathed in water, so there's a cushion aspect to it, and it can lubricate organs and tissues as they move. Water obeys the principle of mass balance. Basically, very simply, what we lose, the water we lose, we have to replace. And that's why and this is sparkling water. That's why they say to be drinking water. But there are multiple factors that impact your fluid balance. Amount of water you drink, amount of physical activity. If you are running, exercising more, especially on a hot day, you're going to lose more water. If you're very sedentary, your body's going to retain more water. Kidney function, the whole chapter on the urinary system. Remember, our kidneys filter our bloodstream and therefore can play a huge role in the amount of water that stays in our bodies. Different medications. There's medications. Some medications cause us to lose water. Some medications cause us to hold on to more water. Uh, different digestive activities. Some of the food that we eat brings water into the body. When we have bowel movements, we lose some water that way. Uh, there are there are times when we can have different problems like diarrhea, which we can lose significant amounts of water through our bowel movements. So an electrolyte, what is an electrolyte? It sounds complicated, but it's not. It's a substance that dissociates in the ions. So one of the simplest ones, think of salt. You can dissociate into Na plus, so a positive sodium ion, and a negative chlorine ion. So substances that dissociate in the ions or charged particles, the sodium, when salt dissociates, the sodium is positively charged, the chlorine is negatively charged, the NaCl. When placed in water, these particles can conduct electricity, and that's what we call them electrolytes. That positive and negative, we can conduct electricity, and we call it an electrolyte. The opposite of that are non-electrolytes, substances that are covalently bonded, do not dissociate into two different charged particles, and therefore, when they're placed in water, do not conduct electricity. All right, so this is showing you an example of just that. Notice the NaCl dissociates into positive sodium, negative chlorine. You put two electrodes in there, and a power source, and electricity will be conducted because of the positive and negative chlorine. Excuse me. All right. Electrolytes are, the term ion differentiates electrolytes from an electrolyte form of an element. Sodium versus the sodium ion are different. Remember, sodium has a positive charge, so it means it's lost an electron versus the sodium in its metal form. So we just want to make sure we're talking about the ion when we're talking about the electrolyte. Electrolyte balance is maintained by principle of mass balance. Must be maintained from diet, equally inputted and released, and several mechanisms help maintain our electrolyte balance, mostly hormonal, which we're going to talk about. But ion concentration is dependent not only on the number of ions in the body, fluid like blood, but also on the amount of water. Remember, these things are dissolved in water, so our fluid balance is going to play a huge role in our electrolyte balance, right? So the concentration of sodium and chlorine ions depends on how much sodium and chlorine ions are in our body, but also depends how much water is in our body. The more water, the lower the concentration. The less water, the higher the concentration, for instance. Okay? So those are going to kind of work together. Acid, base, and pH. So an acid, chemical that dissociates in water to release hydrogen ion. Hydrogen ion, positively charged hydrogen ion, means it has proton, neutron, and has lost its electron. Common acids include hydrochloric acid, HCl, in the stomach, and carbonic acid in the blood. They play a role of a variety of physiological functions, digestion of food. We have an immune response due to that is affected with acids, digestion in the cell, lysosomes work with acids. Also part of the ATP synthesis. Bases are sort of the opposite of acids, chemicals that accept hydrogen ions. And so we see a common one is bicarbonate ion. You see that negative charge, the most common base in the human body. Bicarbonate and other bases are components of the buffer system. We're going to talk about that a little bit later. to resist dramatic swings in hydrogen ion concentrations in the body. So a base, a hydrogen, an acid wants to release a hydrogen ion, and a base wants to accept. Notice that HCO3 negative, and what does it want to draw in? That positive hydrogen ion. So that proton and electron, that positive hydrogen ion, it wants to draw in and connect to that. Remember, opposites attract. pH scale, also don't get tripped up by this, can be very simple. Solutions with a pH less than 7 are acidic. Acidic, that means they are releasing hydrogen ions. An increase in hydrogen ion results in a solution with a lower pH. Solutions with pH greater than 7 are basic. They're accepting hydrogen ions. So their pH is above 7, and then solutions with a pH of 7 are considered neutral. They're not accepting or releasing hydrogen ions. It's neutral, right there in the middle. Human beings are slightly basic, 7.3, 7.4-ish. We are slightly basic, so slightly accepting of hydrogen ions. Fluid homeostasis, part 2. All right, so your total body water. It's a reference based on a standard size human being, about 154 pounds. Water in the body is about 60% of your total body weight for the basic person. And this can differ based on different people. This is just a general standard. Many of you may also know that this is very similar to the standard used on treadmills. So when you go on, I know on the Precor treadmills, when they're calculating calories burned, if you don't plug in your age and your weight, the standard that it uses is roughly the same standard, about 150-pound man. And so that's, if you don't plug in your specific weight and specific age, it's going to consider about a 150-pound man and use a calorie burn based on that. So if you weigh more than 150 pounds, you're probably going to burn more calories than it says. If you weigh less than 150 pounds, you're probably going to burn less. If you're a woman, you're probably going to also burn less. In general, 1 kilogram of water is equal to 1 liter, equals to 42 liters, or total body water of a 70-kilogram man. So 42 liters, 11 gallons is the total body water of a 70-kilogram man. And this can be very different, like we said, based on gender, body mass, age, amount of adipose tissue present, all kinds of things. Where is water found in the body? Good question, right? Intracellular, extracellular, right? Intracellular, inside the cell. You have trillions of cells in your body. Every cell has cytosol. That cytosol is primarily made up of water. So 60% of your body fluids, or 26 liters for the standard man, is considered water. That's where we find 60%. And then we have extracellular, outside the cell, ECF. This could be your blood plasma. This could be your interstitial fluid, the fluid between cells. And so that's about 8% of your blood plasma. Another 30% is your interstitial fluid. And so that's the breakdown of the water in the body. Kind of interesting, right? Blood, as much blood as we have, blood plasma is only about 8% of the water in your body. Most of it is in your cells. That's where we are mostly made of water. I don't know why every time I teach this, I get thirsty. All right, so fluid compartments. The solute composition of plasma and interstitial fluid is similar, right? Your blood plasma, the interstitial fluid around the cells, the solute composition is similar. The main difference is the protein content. Remember, blood plasma has uh, different proteins in it that are not just floating around in your interstitial fluid, which has virtually no proteins. However, the solute composition of the extracellular fluid and cytosol varies starkly. So concentrations of sodium, chloride, calcium, bicarbonate, much higher in the extracellular fluid, the fluid outside the cells, than in the cells, in the cytosol. Proteins and potassium, magnesium sulfate, monohydrogen phosphate have much higher concentrations in the cytosol, right? Remember that sodium potassium pump. So it's going to keep sodium high on the outside, keep potassium high on the inside. Sodium potassium pump. All right, so this is the solute composition of extracellular fluid and the cytosol. So you see how it differs pretty significantly and needs to be that way based on the different reactions that need to happen in the body. And so, how does water move? Well, so remember, this fluid balance is primarily we're looking at water. So, solute movement between compartments is restricted. Water is usually free to move between compartments. The direction that water moves is influenced by two gradients. We've seen these before when we studied the blood system, the arteries, and specifically in the capillaries. Hydrostatic pressure, the force that the fluid exerts on cells, tends to push water away from an area of higher hydrostatic pressure to one of lower. So blood being pumped through the capillary is at a higher hydrostatic pressure than the surrounding tissues when it gets into a tissue bed. At the start of the capillary, the hydrostatic pressure is higher, so fluid is pushed out of capillaries. The blood vessel, the blood cells, the erythrocytes stay in the capillaries, but the fluid is pushed out and eventually pushed into the cell by higher hydrostatic pressure. But then we have another pressure, if you remember, osmotic pressure gradient, force of the solutes in solutions tends to pull water towards solution with higher osmotic pressure, or pull water towards the solution with higher concentration of solute. The solution's automatic pressure is termed by osmolarity, number of solute particles present in the solution. Right, so we have the hydrostatic pressure, which is going to, uh, as we said, of the plasma is higher than that of the interstitial fluid, forces water out of the capillary. When hydrostatic pressure of plasma increases due to higher water volume, more water is pushed out. Increased hydrostatic pressure of interstitial fluid above that of the cytosol, above that of the cell, drives water into the cell. When hydrostatic pressure of plasma decreases, it doesn't normally move backwards, which we know when we studied the bloodstream. Osmotic pressure of the extracellular fluid and cytosol is normally equal, isotonic. So the extracellular fluid, the fluid outside the cell, the fluid in the cell normally have the similar osmotic pressure. But when the solute concentration of the ECF is altered, as osmotic pressure changes, and so its ability to cause water movement by osmosis also changes. If we have higher concentration, if we have lower concentration of solute than the cytosol, lesser ability to cause water movement by osmosis. Cytosol has great osmotic pressure. ECF gains water, and cell in hypotonic ECF gains water and will swell. All right, so if the cell is hypotonic, that means there's a higher concentration of solute inside the cell. Water from outside the cell is going to come in, try to dilute the inside, cell swells. And the reverse happens. If there's higher concentration of solute outside the cell, water will come out, cell will start to crenate, shrivel, right? That's by the process of osmosis. So think about that and make sure it makes sense to you. So the direction of water movement between plasma, blood plasma, and interstitial fluid is determined by force exerted on water by these pressure gradients, right? So high hydrostatic pressure dominates, remember, at the arterial end, pushes water out. High osmotic pressure dominates at the venular end of the capillary bed, draws water back in. Excess water goes into the lymphatic system. Right, direction of movement between plasma, extracellular fluid, and cytosol. Intracellular fluid is also termed by pressure gradients. The ECF hydrostatic and osmotic pressures are similar to the ICF under normal conditions. So little water is moving between the compartments. So between your extracellular fluid and your intracellular fluid. Water gained or lost by plasma influences that extracellular fluid and intracellular fluid, hydrostatic and osmotic pressures. Change in osmotic pressure of interstitial fluid creates gradient that has direct influence on cytosol volume. Hydrostatic pressure increases, makes plasma hypotonic by diluting it, decreases osmotic pressure. You see, so all these things are totally related to each other. Both situations, higher hydrostatic pressure, pressure pushing on the outside of the cell, lower osmotic pressure cause water to move out of plasma into interstitial fluid, which drives water into cytosol. And then during dehydration, hydrostatic pressure decreases. You have less water, so less pressure, leading to less water leaving the plasma, makes plasma hypertonic, increases osmotic pressure. Hypertonic plasma will draw water out of the cytosol, out of the cell, and interstitial fluid and into the plasma by osmosis. Cell shrinks. Right? So these things are just basically saying the same thing, but at the cellular level, at the extracellular fluid, intracellular fluid level. And that's just showing you a diagram and trying to make it make sense. Okay, water intake, normal conditions, what happens when you take water in, more water gets into the cell. When you have releasing more water comes out of the cell. Combination of hydrostatic pressure and osmotic pressure. All right, factors that influence water loss. Majority of water loss daily is through your urine. You go to the bathroom. That makes sense. Now, we have what is called obligatory water loss. So even if you didn't drink any water today, your body still will urinate about 500 milliliters of urine. This is required to prevent toxins from building up and also to balance electrolytes in your body. So, what happens if you don't drink water for consecutive days and you keep keep making 500 milliliters of urine? Well, your body's going to get into some serious trouble eventually because of the amount of water that you're losing just naturally. All right, so there's the obligatory water loss. So just naturally, we lose about 500 milliliters of urine. Your body makes it. It needs to get rid of it every day. We also have what is called sensible water loss. That's 100 milliliters lost in the feces. Insensible water loss, 600 milliliters lost in sweat, evaporation. So total, most people lose about 2.5 liters of water a day. And this can fluctuate based on how hot it is, how much you drink, how much you exercise, all those kinds of things. If we're losing 2.5 liters a day, we need to gain about 2.5 liters of water per day. Right? We can gain water through the reactions that happen in our body, the catabolic reactions in our body. That's called metabolic water, which is 250 milliliters a day. We can gain water ingested from the foods that we eat. There is water in foods that you eat. I had grapes earlier today. Those absolutely have water in them. There's water driven by the thirst mechanism. Your body says, I'm thirsty, and you want to go and drink water, controlled by osmoreceptors in the hypothalamus that respond to changes in your plasma, your blood plasma osmolarity. So that just the fact of being thirsty, you drink about 1,500 milliliters of water per day. Right. So what happens is decreased plasma volume, which results in so if we decrease our plasma volume, think about this. Remember, blood plasma is primarily made up of water. If we decrease our plasma volume, this results in a drop in blood pressure. If a drop happens in more than 10 to 15 millimeters of mercury, it's detected by our baroreceptors in several arteries. This can stimulate our juxtaglomerular cells in our kidneys, remember those, to initiate the renin angiotensin aldosterone system. Ends with the formation of angiotensin 2. The loss of plasma volume and increase in angiotensin 2 both enhance thirst sensation. So blood plasma decreased because there's less water in our blood, causes our blood pressure to drop, which it can be detected by the baroreceptors in several arteries, stimulates the juxtaglomerular cells in the kidneys, which basically enhance our thirst, cause us to drink more water. Therefore, increasing the water in our blood plasma, therefore increasing our blood volume, therefore increasing our blood pressure. All right, so that's just showing you that water losses and gains. Showing you the maintaining homeostasis. So how much water do we need to drink? Well, water intake should balance water loss. Average person loses about 2.5 liters, so they need to gain 2.5 liters. So 750 milliliters of water is gained from food, 250 from catabolic reactions. So we need to drink about 1.5 liters of water every single day. All right? That's how much water we need to drink. Sometimes it is necessary to bypass gastrointestinal system to get fluids into the individuals rapidly. And this can be administered by what is called an IV, intravenous line, IV. All right. So look at that word intra, into, into, intravenous, venous, vein, intravenous line, allowing nearly immediate effect. So an IV consists of a flexible catheter inserted into patient's vein with an external port to which bags of different fluids can be attached. Remember, blood goes from your systemic system to the capillaries to the veins, eventually back to um, the right atrium, where then it's pumped to the lungs and then to the left atrium, left ventricle, and then back to through the systemic circuit. Okay. So if we need to get fluids into the body, the veins are an easy way to do that. Remember, a lot of the body's blood is being sort of stored in the veins as it's working its way back to the right side of the heart, right? So IV is placed in the vein in the upper limb, known as peripheral line. And when intravenous access is required over long term, larger ports may be inserted into the subclavian and internal jugular, known as central lines. But you can get fluid back into the bloodstream directly by an IV, an intravenous line. All that fluid is eventually going to get back to the heart and back into the systemic circuit. Go through the pulmonary circuit and then back to the systemic circuit, back to the body. Now, hormonal regulation of fluid balance. So four hormones regulate mechanisms that ensure water input matches output. Antidiuretic hormone plays the most important role, balancing water intake with water loss, fluid balance. Right? These ADH produced in the hypothalamus, released from the posterior pituitary, acts primarily on the kidneys, cells of the distal tubule and collecting ducts. Remember this from the chapter, the urinary system chapter, can cause the insertion of water channels, actual channels, aquaporins. And so we're putting channels in the plasma membranes of the kidney cells, allowing for water to be reabsorbed from kidneys back into the extracellular fluid by osmosis. Increased ADH leads to more water reabsorption that increases extracellular fluid volume and decreases urine volume. So this water gets reabsorbed, increases the extracellular fluid volume, decreases urine volume, right? Less water lost to your urine. A decreased ADH leads to more water elimination via urine and a decrease in extracellular fluid volume. So ADH activity and osmosis still require presence of a gradient. That's established by our countercurrent system. Go back to our urinary chapter to look at that. But then we still have angiotensin 2, aldosterone, and AMP and their role in maintaining fluid balance. Electrolyte homeostasis. Electrolyte homeostasis. All right, so we already talked about what electrolytes are. They dissociate in water, positive and negative, conduct electric current. Electrolyte. So sodium ions are the most abundant extracellular cation. Extracellular. outside the cell, cation. Sodium, steep ion gradient between cytosol and ECF makes it critical for all electrophysiological processes in the body. Sodium ion concentrations are kept low within the cell. Remember, this sodium potassium pump uses ATP, and due to the low plasma membrane permeability for sodium, prevents leakage back into the cell. So we have this sodium potassium pump that allows more sodium to be outside the cell than inside the cell, so that when sodium channels in the plasma membrane open up, the sodium outside the cell can now rush into the cell following both electrical gradient and concentration gradient. Cell can depolarize. Remember, we talked about depolarization. We talked about neurons and muscles, right? So it's very important to keep that sodium gradient the way it is. Regulation of sodium ion concentration is critical both for that sodium ion balance and fluid balance, as water reabsorption in kidneys depends on the gradient consisting mostly of sodium and interstitial fluid. So here comes angiotensin 2 and aldosterone, the other hormones that we had mentioned earlier that increase sodium retention. Main trigger for the RAAS is low extracellular sodium concentration. AMP decreases sodium and water reabsorption. Angiotensin 2, aldosterone, and AMP together maintain relatively stable plasma sodium ion concentration, right? Blood plasma sodium ion concentration. That sodium concentration is critical. Okay, so these are the maintaining homeostasis for the sodium. Right, so let's look through this. Right, so the stimulus, start at the top. Sodium level in the extracellular fluid decreases below its normal range. Right, so we want sodium levels high outside the cell, so that when that cell, it's time for that cell to depolarize, sodium can rush into the cell. Right, so the stimulus for this problem, sodium levels in the extracellular fluid, the area outside the cells, have decreased below the normal range. Right? So what happens? Receptors in the macula densa, it's in your kidneys, and the nephrons detect the change, activating the renin, angiotensin, aldosterone system, RAS. Right? We've detected sodium levels are low. We've activated the RAS. Juxtaglomerular cells in the kidney release renin, which leads to the production of angiotensin 2 and angiotensin 2. Angiotensin 2 stimulates aldosterone, released from the adrenal cortex. What happens? The angiotensin 2 leads to increased sodium reabsorption, right, in the proximal tubule of the nephron. So we're reabsorbing more sodium, not releasing it into the urine. That's what the angiotensin does. The aldosterone release from the adrenal cortex leads to increased sodium reabsorption from the distal tubule of the nephron. So one is increasing reabsorption of sodium in the proximal tubule and one in the distal tubule. But the goal is the same. We're reabsorbing more sodium. So less sodium is being lost to urine. And as you see the result, the sodium level returns to normal. And then the angiotensin 2 and the aldosterone secretion decrease. Okay? Very important. You can have sodium ion imbalances, hypernatremia, elevated sodium concentration, or hyponatremia, decreased concentrations of sodium, right? Elevated concentration of sodium, look at that, is normally caused by dehydration. So you have less water, same amount of sodium, the concentration of sodium goes up. Versus hyponatremia, you have overhydration, more water, same amount of sodium. Now your concentration of sodium goes down. And this can happen from numerous different uh, things in the body. Dehydration, not having enough fluids, surgeries can cause these problems. Different medications can cause these problems. Potassium. Potassium, the most abundant intracellular. So we have this sodium potassium pump, remember, which is pumping sodium out, potassium in against their concentration gradients. So potassium is the most abundant intracellular cation. You see the concentrations there. Potassium moves out of cell against its concentration. Potassium moves out of cell against its concentration gradient through plasma membrane channels as main mechanism of repolarization phase of action potential. Right, so the action potential, we have that sodium rushing in, we reach our threshold, we spike, but then we repolarize, which is critical for returning excitable cells to their resting membrane potential. We need to have sodium move out. Potassium move out. And so we have to maintain this potassium ion concentration. And there are several mechanisms within the endocrine and urinary system that help with that. Insulin, aldosterone, epinephrine stimulate uptake of potassium by cells. Excess potassium is secreted in your urine and excreted from the body. Makes sense. Potassium ion imbalances result when excess potassium is taken in or lost. It can be affected also by your water imbalances. Hyperkalemia, when you have too much potassium, very dangerous. Potentially fatal electrolyte imbalance because it makes your resting membrane, if you look at this chart here, makes your resting membrane, your resting membrane potential of excitable cells more positive, rendering these critical cells incapable of functioning normally. So potassium is positive. If I have excess potassium, makes my resting membrane potential too positive, and then I don't get this depolarization that happens. If I'm too positive at rest, then I don't get this depolarization that needs to happen for a neuron to be excited or for a muscle to be excited. The reverse is hypokalemia. It can be caused by different diuretics, lead to excess potassium loss in your urine, makes so you have less positive potassium inside the cell, makes the resting membrane potential more negative, leaving excitable cells hyperpolarized and less responsive to stimuli, right? So if I have less potassium, that means instead of my resting being at resting membrane potential being at -70, it will be even lower. So it would take even more to generate that action potential. So I'm hyperpolarized, take even more to generate that action potential. So there would be a less likelihood of a response to stimuli. Hope that makes sense. So if I have too much potassium, I'm not at negative 70, I'd be at maybe negative 30, and it will be I could or negative whatever, negative 60, let's just say. And it would be a lot easier for me for my cell to be excited. It'd be too quick to get excited. If I have too little potassium, then it would be a lot harder for the cell to get excited than normal. All right. Acid base homeostasis, also very important. So normally, as I've mentioned before, we must maintain pH about 7.35, 7.45, making us slightly alkaline. Slightly, when you see that word alkaline, don't get totally thrown off by it, but just think of slightly basic. So blood pH is maintained by our respiratory system, urinary system, and buffer systems. So we have chemical buffers uh, that buffer body fluids and physiological buffers, which rely on functions of organ systems to buffer fluids. Different ways we can do it. So acids and bases are either formed during normal metabolic processes or they are ingested in our diet. We can eat diets that contain acids and bases. Main source of metabolic acid is carbon dioxide. Remember carbon dioxide, um, byproduct of glucose metabolism. One of the reasons we breathe out uh, carbon dioxide. It is a volatile acid capable of changing states and solution from CO2 gas to carbonic acid and back, so that carbon dioxide can be eliminated from the body, both from the kidneys and the lungs. We also have lactic acid. Think about that when you work out, for instance, metabolic acid formed as a byproduct of glycolysis. Uric acid, catabolism of nucleic acids. You have acidic ketone bodies formed by fat catabolism, breaking down fat and using it as an energy source. You also have fixed acids. Acids that are unable to change to gaseous states must be eliminated by kidneys. A diet is a rich source of both acids and bases. Now you can read this slide if you would like about the alkaline diet. We don't have to worry about this right now, but be careful when it comes to people saying that, oh, we should eat diets that are this. You should drink, 2 gallons of water a day. You should eat alkaline diets, all these kinds of things. Do your research to make sure what you're doing really is good for the body. So how does the chemical buffer system work? All right, so the chemical buffer system body consists of weak acids. A weak acid is an acid that doesn't want to give up a whole lot of hydrogen ions at a time. Because it's a weak acid and it's conjugate weak base. Weak base doesn't want to accept a whole bunch of hydrogen ions, which help. But this chemical buffer system, this combination of weak acid and weak base, help the body to resist large swings in the pH. So when a strong acid is added to the solution, weak base of the buffer system binds to release hydrogen, removing them from the solution. When a strong base is added, the weak acid of the buffer system releases hydrogens, binds to the base ions, and sort of keeps everything where it's supposed to be. Buffers. So that means we don't want it to get too acidic. If an acid comes in, we don't want it to get too basic. If more base comes in. The idea of a buffer is we want it to everything to stay sort of the same. Homeostasis. Let's stay right here, homie. All right, so this is the diagram of that. All right, so we add in the acid. It binds to our weak base. We add in the base. it binds to our weak acid. And that's how a buffer system works. So that neither an acid or a base entering the system changes the overall pH too much. In the body, we have the carbonic acid bicarbonate ion buffer system. Consists of carbonic acid, a weak acid, and its weak conjugate base, bicarbonate. So when CO2, but carbon dioxide, reacts with H2O, water, in your erythrocytes, your blood cells, carbonic acid is formed. You dissociate into a hydrogen ion and a bicarbonate ion. Bicarbonate ion can interact with other hydrogen ions released by strong acids so that your pH doesn't drop too low. The hydrogen ion of that the hydrogen ion from that carbonic acid can react with strong bases so that your pH doesn't go too high. Carbonic acid bicarbonate ion buffer system. We also have a phosphate buffer system, which is dihydrogen phosphate and its conjugate base, hydrogen phosphate. Each component resists changes created by addition of acids and base to the cytosol and kidney tubules. And you also have a protein buffer system, carboxylic acid groups. Various protein buffer systems in the cytosol, such as hemoglobin and erythrocytes, hold 60 to 70% of the body's total buffering capacity. All right, so there's different ways that we can buffer the body. So prevent the big picture idea, prevent the body from becoming too acidic or too basic. We also have physiological buffers, right? So systems allow maintenance of slightly alkaline, slightly basic pH by ensuring adequate number of base ions in body fluids and providing the mechanism for the elimination of hydrogen ions. So respiratory system controls the amount of volatile acids in your extracellular fluid, while urinary controls the amount of fixed acids and bicarbonate ions in your extracellular fluid. Your respiratory system, the lungs directly control your CO2 levels in the blood and also control amounts of both carbonic acid and hydrogen ions. So normally, the amount of carbon dioxide expired by the lungs matches amount made by metabolic reactions happening in your cells. But your respiratory rate can increase during physical activity as glycolytic and oxidative reactions occur more rapidly. During periods of rest, these chemical reactions are reduced and your respiratory rate decreases. So when you're exercising, more carbon dioxide is being formed, more of it needs to be released. Our respiratory rate needs to increase, one of the reasons. And vice versa. If we're at rest, we can reduce our respiratory rate, reduce our exhaling of carbon dioxide, and therefore keep our pH system balanced. Right? Because this system influences the amount of bicarbonate in plasma as carbonic acid formed in the erythrocytes dissociates into hydrogen ion. It's buffered by the hemoglobin, leaving bicarbonate free to be released into plasma. right? So breathing out, especially releasing carbon dioxide, it's going to affect the levels of carbonic acid in our bodies and eventually and thus affect our pH. Urinary system, very similar. Kidneys work with the lungs in two ways. The kidneys excrete fixed acids that the lungs cannot, and they contribute to acid-base balance by controlling bicarbonate ion concentrations in the blood. Right, so your kidneys can manufacture new bicarbonate ion when pH of blood becomes too acidic, and they can secrete and eliminate bicarbonate ions when blood becomes too basic. All right, so we can have different acid-base imbalances occur when these mechanisms are unable to cope with added acids or bases, or a pH gets out of the normal range. So the body will attempt to correct acidosis, becoming too acidic, or alkalosis, becoming too basic, so pH too high, or acidosis, pH too low, through both respiratory and urinary. Um, so respiratory and urinary compensation. But these mechanisms are incapable of completely correcting pH. You can have other issues, other problems. So acidosis is pH of less than 7.35. More, what is an acid? Releasing a hydrogen ion. So acidosis develops when more hydrogen ions are added than buffer system can bind. Acidosis causes neurons to become less excitable. So it can lead to signs and symptoms of nervous system depression. But the goal is going to be the same, to try to fix it, try to reduce the number of hydrogen ions and increase the amount of base ions. Respiratory acidosis, defined as decrease in pH of body fluids due to excess carbon dioxide. So, cause when ventilation decreases, you don't exhale enough carbon dioxide, hypoventilation can lead to a shift that favors production of carbonic acid, lowering of blood pH. This can happen when you're not breathing well, blockage of air passages in lungs. Uh, if anybody's ever been trained in cardiopulmonary resuscitation, you know that breathing is very important. Oxygen, we want oxygen to get to the brain, but we also want carbon dioxide to get out of the body. Metabolic acidosis and compensation, defined as addition of hydrogen ion to the extracellular fluid from acids other than CO2, can be caused by addition of metabolic acids, ketones, uric acid, lactic acid. We also have diabetic ketoacidosis, increase in that hydrogen ion in blood causing pH to decrease, excess metabolic acid. And this can be due to the failure of the kidneys to secrete hydrogen ions into the filtrate, can lead to excess hydrogen ions in the blood, which will decrease our pH. Diarrhea can cause this. And then there's hyperventilation, the first way that we compensate as your body is trying to get rid of that CO2, eliminate that CO2 to lower the hydrogen ion level in the blood and increase your pH level. All right, so you hyperventilate, breathe really fast to try to get more CO2 out. There's also renal compensation. So normal renal function can compensate by increasing the amount of hydrogen ion eliminated via secretion and increasing the amount of bicarbonate ion resorbed. From the filtrate. You also have the reverse, alkalosis. Body becomes too basic. Occurs when more base ions are added than buffer can handle. Your buffer system can handle. Increases the excitability of neurons, causing them to fire action potentials inappropriately. Can lead to tingling, motor symptoms, seizures, coma, death. Respiratory alkalosis and compensation caused by loss of CO2 through lungs due to hyperventilation. So too much CO2 being lost causes you to become too basic. The compensatory, or the way our body compensates, response to this physiological respiratory alkalosis involves excretion of bicarbonate ions and retention of hydrogen ions from the kidneys. Metabolic alkalosis and compensation is caused by loss of hydrogen ions or excess of a carbonate ion. Hydrogen ion loss is commonly due to prolonged vomiting, loss of stomach contents, right? So think of vomiting, think of stomach, think of acids in your stomach. If you vomit a lot, you're getting rid of a lot of acid. Therefore, your body is going to become more basic. Also can be caused by specific diuretics or excess aldosterone levels increase sodium ion with concurrent hydrogen ion loss. So specific diuretics can cause water loss in your body, excessive aldosterone levels increase. Compensation for this is both respiratory and renal. And so the respiratory response to decreased hydrogen ion concentration is hypoventilation. So instead of breathing fast, you're breathing slow, which is going to retain more carbon dioxide and increase your hydrogen ions. Also, the kidneys can retain more hydrogen ions and secrete more bicarbonate ions. So once again, the respiratory and the urinary system work together. So as a clinical tool, we have what is called arterial blood gases. Clinical tool used to assess and monitor patients' acid-base balance. So the arterial blood in your systemic system is used to measure your pH, your PCO2, and your blood carbonate level. So the both type of acid-base imbalance and degree of compensation can be surmised from this test, right? Which makes sense. We're going to measure the pH, the amount of hydrogen ions, the CO2 levels, and your bicarbonate level, that buffer system level. So if we're in respiratory alkalosis, we exhibit elevated pH but low partial of CO2, low bicarbonate ion level, indicates partial compensation by the kidneys. During metabolic alkalosis, exhibits elevated pH, so high pH, That means we're basic. High bicarbonate ion levels, elevated partial pressure of carbon dioxide levels indicate respiratory response leading to partially compensated metabolic alkalosis. Okay, that's just a summary of all of those. Thank you for listening.